Good morning, good afternoon, everyone. Still class is going on, or what? Only 38, 37, 37 have joined yet. Am I audible or not? Let me know, please.
Yes,
Yes, so
sir.
the class is over. The previous class is
Class
over.
is over. Okay, but still 39, 38 have joined yet. So in the last class, we have discussed about the law of total probability, if you remember. This one. Am I right? Yes, no.
Yes, sir.
Okay. So we have discussed about total probability where we discussed that if you have some A1, A2, AK number of mutually disjoint and exclusive, these events A1, A2, AK are mutually exclusive, means disjoint, and exhaustive. So mutually exclusive means if you take the intersection, it is going to be phi, means a null set that will not contain any event point or sample point. And exhaustive means if you take the union of all of these events A1, A2, AK, this will be the entire sample space. I have given you the proof of this theorem in the last class. You can see there in this part. This part is actually proof of that. So let me discuss one problem that is related to this total law of total probability. Okay, wait a minute, let it open. So the problem is like an individual has three different mail IDs. Example is like an individual has three different mail IDs or email accounts. Let me write email accounts. Okay, and most of uh, messages, in fact, 70% come into account number one. Account number one. So an individual is having three accounts, three mail accounts, email accounts, and 70% of all the mails comes in into the first account, and whereas 20% come into account number two. Account number two. And what is left? 70, 20, 90, and rest 10%, and the remaining 10% comes into account number 10% into account number 3. Of all such messages, all the messages into account 1, account number 1, 1% are spam. 1% are spam. Whereas the corresponding percentage is for accounts number 2 and number 3 are 2% and 5% respectively. Okay. So 3 accounts, 70% messages coming in account 1, 20% in account 2, and 10% in account 3. And out of those mails, 1% in account 1 is spam, 2% in account 2 is spam, and 5% in account 3 are actually spam. So the problem is, what is the probability? What is the probability that a randomly selected message is spam? That a randomly selected message is spam. Any suggestion? What can be the scenario? So to use that total probability, first we have to actually give some notations. So let AI denotes message is from account I. Message is from account I. Or let me write account number I. Means what? Where I can be 1, 2, 3. Because there are 3 accounts, 3 email accounts. So if I equal to 1 means message is from account number 1. If it's A2 means I equal to 2, then it will be A2. And that is an event that message is from account number 2. If I equal to 3, then message is from account number 3. Further, I will consider another event that the message is spam. Message is spam. Got it? So what we have from this given problem? We have given. What are the given things? Probability of A1. Can you please tell me the probability that message is from account number 1? 70% come into account number 1. So that probability is 0.7. Then probability of A2, that the message is from account 2. 20% comes into account, so it's 0.2. Similarly, probability of A3 is 0.1. right?
Yes, sir.
Yes, sir.
Next, suppose it is given that it is from account 1, then what is the probability that it is spam? Spam, given that this is from account 1, it's 1% of the first account. The messages into account 1, 1% are spam. So this is 1%. So this probability is going to be 0.01, right? Then what is the probability that it is spam and it is given that mail is from account 2? It's 2%, so 0.02. Similarly, the probability that it is spam and it is given that it is from account number 3, this is 5%, so this is 0.05. So can we use the law of total probability? So from the law of total probability, what we have, we are interested in finding that probability that a randomly selected message is spam. It may be from first account, it may be from second account, it may be from third account. So that is actually probability of B. B is an event that message is spam. So probability of B is needed actually. So that we can get from probability of B given A1 into probability of A1. Means probability, it is given that it is from account 1 and this is also a spam. Then probability that this is spam and it is given that it is from account 2 and probability of 2 plus probability of, let me write it here, probability of B, it's a spam and it is given that it is from account 3 into probability of A3. So can you calculate this value, probability of B? You have all of these values, whatever there in this expression. So probability of B given A1 is this one, 0.01 into probability of A1, 0.07. First part plus second part is probability of B given A2, this one. So it is 0.02 into probability of A2, it is this one, 0.0, 0.2 actually, not 0.0. 0.2. And for the third part, probability of B given A3 is 0.05 into probability of A3 is 0.1. Got it?
Yes,
You just give me the value.
0.012.
so
0.
0.016.
0.016.
Yes,
Okay, it's 0.016. 0.016. So this is the probability that the message, a randomly selected message, is spam. So can I say that actually in long run means if you stay repeating the process, you selected one, whether it is spam or not, you selected again one, whether it is spam or not, you selected again. If you see in long run, so in long run or by repeating the process multiple times, 1.6% of the messages are spam. That's what it means. Got it? Any question? Let me know. If not, let me go to the next slide. One minute, let it open. Let me this color. Fine. So next is definition of Bayes theorem. So let me plot one diagram kind of thing. Suppose you have k events, A1, A2, AK, which are mutually exclusive as well as exhaustive. Means this is the entire sample space. You are dividing the sample space into some mutually exclusive events. These are mutually exclusive events because nothing is common in any two of these. Clear? Suppose this is A1, this is A2, and so on. This is some A, K, which are actually mutually exclusive. This and this, if you take the intersection of A1 and A2, nothing is common. Okay, no intersection part is there. So let me define it like let A1, A2, AK be a collection of be a collection of K individuals. Or instead of that, I can say K mutually exclusive. Let me add K mutually exclusive. Mutually exclusive and exhaustive events with prior probabilities. I will discuss this term prior probabilities. Suppose P of AI. I'm writing P of AI. This I can be 1 to up to K because K events are there. So for I equal to 1, it's A1, and that's the probability of that event A1 is probability of A1, P A1. Similarly for A2, it's PA2. For A3, it's PA3. Then for any other, then for any other event B, for which probability of B is always greater than 0, the posterior probability probability of AJ of any event AJ is given, or of AJ with this event B is given, okay? AJ given that B has already occurred, that B has occurred is, means what? If this is the sample space A1, A2, A3, these are actually the collection of mutually exclusive and adjunctive events. Then suppose I am having any other event A, other event B. This circle is any other event. Then the probability of AJ given this event B is probability of AJ given B denoted by this is equal to probability of AJ intersection B by probability of B, that you can rewrite as probability of AJ, or let it actually AJ is the prior, so it will be B given AJ into probability of AJ divided by the total probability of B, and that is nothing but summation j equal to 1 to k probability of B given AJ into probability of AJ. So this is the Bayes statement of Bayes theorem, which actually is very famous because of its ability to incorporate the prior knowledge to the estimation process. Means if you know something, you can use that to predict the future one. Means here you can see that A1, A2, AK, their probabilities are known. It's prior probability, I'm calling it prior probability, means they are already known actually. They are known in advance. Then you can use this probability A1, A2, AK, and then you can find the probability that of any of these events for future A1, A2, AK, given that some other event B has already occurred. So this is the formula for this Bayes theorem. Let's see one example that will actually make you more clear about this. So let me go to the next. How many students are there? 52. Only 52. At the end, they will join. So let me take the attendance first, and I'll go to that first problem then. Zero zero 007 5138 5171
Present, sir.
237
Present, sir.
273
Present, sir.
308
Present, sir.
534
Present, sir.
622 652.
Present, sir.
Present, sir.
Then 768 768 If you are having mic issue, you write in the chat box at the same time. 768 1053 1158 1274
Present, sir.
1510
Present, sir.
1533
Present, sir.
1561
Sir, he is present.
1565.
Present, sir.
Okay. 1565 present. Okay. 1581
Present, sir.
1596
Present, sir.
1598
Present, sir.
1599
Present, sir.
1617
Present, sir.
1746 1792 1792 1799
Present, sir.
1821
Present, sir.
1855 1855 1864
Present, sir.
1970 1970 2016 2039 2040 2246
Yes, sir. Present.
2406
Yes, sir. Sorry, sir. 2406 is present and 2246, I don't know.
246 2411 446
Present, sir.
2461
Present, sir.
2461
Present, sir.
okay 2605
Present, sir.
Sir, 461 answered.
261
Sir, 2461 I answered.
461 answered
Yes.
2637
Sir.
2649
Present, sir.
2669
Present, sir.
2673
Present, sir.
2677
Present,
2679
sir.
2682
Yes, sir.
2683
Present, sir.
2709
Present, sir.
2720 2720
So he raised his hand.
chat box chat
Yes, sir.
2722
Present, sir.
2725
Present, sir.
2731
Present, sir.
2739
Present,
28
Present, sir.
2823
Present, sir.
2853
Present, sir.
2863
Present, sir.
3203
Present, sir.
3205
Present, sir.
3210
Present, sir.
3212
Present, sir.
3213
Present, sir.
3218
Present, sir.
3223
Present, sir.
3232 3232 3237
Present, sir.
3242 3242 3250
Present, sir.
3336
Present, sir.
3340
Present, sir.
3345 3346
Present, sir.
3362
Present, sir.
3368 3382
Present, sir.
3383
Present, sir.
3325
Present, sir.
Sir, 242.
2246 present.